Now we understand what a differential equation is. Of course, when you write an equation, usually what you want is a solution to the equation. And for a differential equation, remember the unknown thing is a function. So a solution to a differential equation is a function, and we'll require it to be a continuous function, that satisfies the equation. In other words, it makes the equation true. To see how this works, let's try to guess a solution to this differential equation. So dy dx equals 2 times y. Now, we don't really have any techniques for calculating solutions to differential equations at this point, but what we can do is use one of the most time-honored traditions in math and just guess an answer and then see if it's right. So to guess a solution to this equation, what we need to do is think up a function y whose derivative is twice itself. Well, actually having this 2 here makes it a little harder, so maybe before we guess a solution to dy dx equals 2y, let's guess a solution just to dy dx equals y. Can you guess a solution to this equation? Can you think of a function whose derivative is equal to itself? Sure. There's a function that we're very familiar with that's equal to its own derivative, and that's e to the x. Now that we have this in mind, we could check that this is a solution by plugging it into this equation. We would get derivative of e to the x dx equals, and we're going to check, is this equal to e to the x? And yes, it is. Those are equal. So e to the x really is a solution to dy dx equals y. Okay. Well, now let's come back to our original equation, dy dx equals 2y. Well, let's see. This 2 here probably just comes from a constant in this e to the x somewhere. Can you think of a way to modify this e to the x function so that when you take its derivative, you get an extra 2 in front? It seems like maybe we could use e to the 2x. Well, let's check. One of the nice things about solving an equation is if you think you have a solution, you can always just plug it back into the equation to see if it really works. Of course, to plug this function, y, into the differential equation, we'll need to calculate the derivative of y. So dy dx is 2e to the 2x. And now we can plug all this into the differential equation and see if it's true. So dy dx is 2e to the 2x. And we are checking, is that equal to 2 times y? And y is e to the 2x. Yeah, those are the same. So y equals e to the 2x really is a solution to our differential equation. Also, it's continuous. Remember, solutions have to be continuous. But there's something funny about differential equations. This solution that we guessed here, you actually might have guessed a different solution. So e to the 2x did work, but what about, well, what if we put some number in front here, where this number, capital A, is just a constant, any constant? Would it still be a solution? Well, let's check. If y is a times e to the 2x, dy dx is a times, and then with the chain rule, we get a 2, e to the 2x. And then we can take these two and plug them into the differential equation. Remember, the differential equation was dy dx equals 2 times y. So plug these in. We get a times 2e to the 2x. And we want to know, is that equal to 2 times y? And y is a times e to the 2x. Are these equal? Yes, those are equal. So we didn't find just a single solution to this differential equation. We found a whole bunch of solutions. In fact, infinitely many solutions, because capital A could be any constant at all. So it's a whole collection of solutions. This kind of collection of solutions, where they're all They're all related by some constant that you can pick. This is called a one-parameter family of solutions, where capital A is the parameter that takes you from one solution to another. So for differential equations, we can guess solutions, and if we have a guess, we can check if our guess is correct. And also for differential equations, we will see that getting lots of solutions like this is not an uncommon situation. In fact, most differential equations have infinitely many solutions. And when we solve a differential equation, we will always try to find all of the solutions and not just one or two. All right, let's look at another example. Okay, so here we have a differential equation, dy dx minus y over x equals minus x sine x. And let's verify that this is a solution, y equals x times cosine x. Just for the record, let's check what is the order of this. Well, the order of a differential equation is the highest derivative that shows up, and that's the first derivative in this case. And is this linear? Let's see, it's got a derivative, first derivative of y, minus, we could write it like this, 1 over x times y equals minus x sine x. So we have derivatives of y multiplied by functions of x all added up. And so yes, it's linear. Okay, so we have what is supposedly a solution, y equals x cosine x. And we need to verify that this is a solution. So if you think you have a solution to an equation, how can you check that it is a solution? Just plug it in, just check. So to plug this function y into the differential equation, we're going to need to calculate its derivative. So let's do that first. dy dx is, so got to use the product rule here, cosine x minus x times sine x, and then plug all of this into the differential equation. So differential equation says dy dx, which is cosine x minus x sine x minus 1 over x times y, so minus 1 over x times, and y is x cosine x. And we want to check, is this equal to minus x times sine of x? Well, let's see, we're going to have to do some simplifying here. So it looks like this x cancels that one, but then here we have a plus cosine x and a minus cosine x, and so those cancel, and we're left with minus x sine x and minus x sine x. So yes, those two sides are equal, and so this supposed solution, x times cosine x, really is a solution to the differential equation. One thing we don't know is whether this is the only solution to the differential equation. Based on what I said before, you might guess that it's not the only solution, and you'd be right. But at this point, we don't have any tools for finding other solutions to this differential equation.